Alright, so today we're going to talk about states of matter and phase change. So to start off with, everyone I hope is familiar with gas, liquid, and solid states of matter. So this gives you a brief overview of what we think of when we think of gas, liquids, and solids. So we know that gases conform to the shape and volume of their container. They take up the entire space. Liquids take up the shape of their container, but they have their own volume and their own surface. And then solids have their own volume and shape and do not necessarily mimic that of their container. Now, the two different characteristics of gas, liquids, and solids that we're going to focus on today are compressibility and ability to flow. And both of these have to do with intermolecular forces that we talked about last time. The first one, compressibility, has to do with how well we can compress two gas molecules together. So if we think about gas molecules in a container, they spread out very far from each other and they have very little interaction with each other. So we say they have high compressibility because there's not really intermolecular forces there. They're not close enough to interact, so we can push them closer together. For liquids, though, the molecules or atoms are interacting through the intermolecular forces, whether that's hydrogen bonding or dipole-dipole or London dispersion forces, so we can't really push them together anymore. They have very low compressibility. I can't compress 5 liters of a liquid into 1 liter. It's not going to work. And for solids, we even have less compressibility. They are in a tightly formed lattice, and through the intermolecular forces, they're as close as they can get to each other. So we can't really compress them anymore. In fact, adding any more pressure to them is likely to cause them to break or crack or crumble, or even shatter. The second characteristic we want to talk about is ability to flow. Ability to flow goes back to the idea of viscosity. The molecules have to flow around one another. And this is based on intermolecular forces. Now, in a gas where the molecules are not interacting at all, we have very high ability to flow. There's nothing keeping them tied to a neighbor. In a liquid, there's moderate ability to flow because they are interacting with their neighbors. So there's those intermolecular forces we have to worry about. The stronger the forces, the less ability to flow they have. And in solids, there's almost no ability to flow. The molecules are locked into a lattice position and can't really escape their neighbors. So whether something is in the gas, the liquid, or the solid phase really has to do with two types of energy. One we've been talking about in the previous lecture and this one, the intermolecular forces. And this is what we call attractive energy. The energy that's connecting the two neighboring molecules, whether that's hydrogen bonding, dipole-dipole, or London dispersion forces. The second type is kinetic energy. This is the energy that's distributed through all the molecules in a substance. Now we talk about average kinetic energy instead of individual kinetic energy because every molecule or atom has its own amount of kinetic energy. So we talk about the average over the entire substance. But this is the energy that a molecule or atom has to move, or vibrate, or shake within its position. So looking at these two energies then, both of them are important to understand to determine the phase. If the average kinetic energy is greater than the attractive energy, or intermolecular force, that means the individual molecules have a greater energy and they are separated from their neighbors. They really have no attraction to their neighbors and no interaction. So this is gas phase. If your average kinetic energy is less than the attractive energy or the intermolecular force energy, then it's in the solid phase. That means you're more attracted to your neighbor and you have very little energy for yourself. Anything in between the gas phase and the solid phase is considered the liquid phase, which can vary dramatically depending on the substance. So if we have less attractive energy, but stronger kinetic energy, we're in the gas phase. So the individual molecule or atom has more freedom to move around, almost no interaction with neighbors. Stronger attractive energy but less kinetic energy means the attraction to the neighbor is stronger and the molecules cannot escape their neighbors. So that's the solid phase. And liquid can be anywhere in between here. Now, of course, we know that the phase of a substance can change, and the two biggest factors that can affect this change are temperature and pressure. So we know if we change the temperature, we can condense a gas back into a liquid, we can freeze a liquid into a solid, and then we can sublime a solid back into a gas. We can also deposit a gas into a solid directly without going through the liquid. We can melt a solid into a liquid, or we can vaporize a liquid into gas just by changing the temperature or the pressure. So these 6 different terms for phase change are going to be very important, and you need to know these 6 terms. Melting is referred to as fusion when we talk about these phase changes. So how do we condense a gas into a liquid? What change in temperature needs to occur? So if we think of this in terms of those 2 types of energy, the kinetic energy and the attractive energy, in order to condense a gas into a liquid, we need to push those gas molecules closer together. We need to decrease their kinetic energy and increase the attractive energy between them. So if we're removing the energy, we are usually decreasing the pressure and the temperature. Right, vaporization is the first one we're going to talk about. So when we vaporize a liquid into a gas, we are changing the kinetic energy and the attractive energy. Alright, so let's again think about the 2 types of molecules in a liquid based on position. We have the molecules on the inside with neighbors above, below, to the sides, so they're being pulled in all directions. And then we have the molecules that are on the surface. Now the molecules on the surface have less attractive energy based on having less neighbors. So therefore less energy is required to vaporize those liquid molecules on the surface. So only molecules on the surface get vaporized. So the rate of vaporization is then dependent upon the surface area of the liquid, if only those surface molecules can vaporize. It's also dependent upon intermolecular force, because this tells us how much energy we need in order to vaporize the molecule. The stronger the force, the more energy is going to be required. And then it's also dependent upon temperature. Like we've talked about previously, if I increase the temperature, I'm loosening up those intermolecular forces. Alright, so if we look at our different pictures at the bottom, the first picture shows vaporization, so liquid molecules on the surface becoming gas molecules as we get that extra kinetic energy necessary to escape the neighbors. In the second picture, we also see some of those gas molecules condensing back down into the liquid phase. So when this happens, we have molecules being vaporized as well as being recondensed. In this case, in picture B, the vaporization rate is still greater than condensation rate, so we have an increase in vapor pressure. Eventually, though, as more vapor is released, the condensation rate will begin to equal the vaporization rate. Now, vaporization rate is dependent upon temperature. As we increase the temperature, we loosen up the intermolecular forces, and it increases the rate of evaporation. Alright, so if we look at the diagram down here, we have fraction of molecules along the Y and kinetic energy along the X. So what this is showing is that for a given temperature, if we look at the blue line first, we have a certain amount of molecules that have very little kinetic energy down this end. We have a large number of molecules that have a moderate amount of kinetic energy. And then we have a smaller group of molecules that have high kinetic energy, and an even smaller group that have the highest kinetic energy of the sample. Now the dotted line indicates the energy needed to vaporize. So only these molecules that are to the right of this dotted line but under the blue curve have sufficient energy to escape their neighbors. So these would be the molecules that could actually vaporize, that are shown in the shaded region. Now if we increase the temperature, we're increasing the kinetic energy of all the molecules, so we overall see this graph shift to the right. We still have some molecules with very little kinetic energy. We have more with a higher amount of kinetic energy, and then we have a small amount with the highest amount of kinetic energy. But again, our dotted line isn't moved, and we're looking at the shaded region to indicate the molecules that have sufficient energy to escape their neighbors and vaporize. And if we increase this temperature again, we would see an even further shift to the right, and even more molecules would be able to vaporize. Condensation is the opposite of vaporization, where we have those gas molecules condensing back down into the liquid. In order to do this, they have to lose some of their kinetic energy, and this is usually through temperature changes. By lowering the temperature, the kinetic energy is less, and the molecules are slower when they move around and clump back together into the liquid phase. Now, the vaporization and condensation rates are going at the same time, and we call this a dynamic equilibrium. Dynamic meaning that we constantly have both of these processes occurring. Molecules are vaporizing from liquid into gas, and they're also condensing from the gas into the liquid. Once it reaches the point where the rates of these two processes are equal, we've reached an equilibrium. So if we think about having a flask that has a stopper on it, we have some amount of a liquid inside the flask, but no gas. So it says vacuum, so all the gas has been removed. Since there is no gas molecules, the only thing that can happen is vaporization. So our liquid molecules begin to vaporize, and some of the liquid molecules become gas. As they then move around the interior of the flask, bouncing against the walls of the container and each other, some amount of them will begin to condense as well back into the liquid. So we will have vaporization and condensation happening at the same time, and eventually the rates of these two processes will be equal. Because there's a stopper, the gas cannot escape. The picture on the far right shows this relationship in terms of a graph. So we have vapor pressure on the y, and we have time on the x. So as time increases, as it sits in the flask, the vapor pressure increases because we have liquid molecules vaporizing into gas. So our pressure of our gas increases and continues to do so as long as vaporization has a greater rate than condensation. But eventually we see that the graph starts to reach a plateau. This is where the two rates are the same. The rate of the molecules vaporizing is equal to the rate of condensation. So at this point where our graph is flat, we've reached an equilibrium. And as long as nothing changes about the environment of the flask, the rates will stay exactly the same. Now this is dynamic because both rates are still occurring, both processes are still occurring, we haven't stopped anything, but because they're occurring at the same rate, we don't see any changes in the amount of vapor pressure. Alright, so let's look at an interesting idea about equilibrium. So if we look at this first picture, we have liquid at the bottom, so we have 6 liquid molecules, and then we have 3 gas molecules above the liquid. If we're at equilibrium already, our rate of our vaporization is equal to our rate of our condensation. But now let's take the vapor off. If we remove the vapor, the only thing left is vaporization. So some of our liquid molecules can become gas molecules. And here we have 4 liquid molecules left after 2 of them have now become gas molecules. Now we've reached an equilibrium again, where our vaporization rate is equal to our condensation rate. Now if you'll look at the equilibrium established at the end compared to where we started at the beginning, you'll notice a similarity. Even though we don't have the same number of molecules, because we removed some vapor in step 2, we have the same ratio of molecules. So over here we had 3 gas molecules compared to 6 liquid molecules. Once equilibrium was restored, we now have 2 gas molecules to 4 liquid, which is the same ratio. So 3 to 6, or 1 to 2, is the same as our 2 to 4, or 1 to 2 ratio. So equilibrium is actually a ratio of our 2 populations. Because we can't get the same number of molecules we had initially as some were removed, we can't restore the same number, but we can restore the ratio. So if we look at vapor pressure, how much vapor is released above a liquid or above a solid, it is of course based on temperature, as we've seen, and it is also based on intermolecular forces. So in this picture we have water, then a vapor pressure along our y in atmospheres, and our temperature along our x-axis in Celsius. So as we increase the temperature, the amount of vapor pressure is going to increase. And it increases as we loosen up those intermolecular forces. More gas molecules are able to escape their neighbors. But it's not a linear relationship. It's normally an exponential relationship. And it varies depending upon the intermolecular forces. Now we know water has hydrogen bonding, which is a fairly strong intermolecular force. So if we compare that to other chemicals at the same temperature, we can see the difference in vapor pressure. Water is down here at the bottom with the least amount of vapor pressure. Ethyl alcohol has a little bit more vapor pressure, and we can actually smell the gas vapors from alcohol. Bromine has even more vapor pressure. You can actually see bromine vapors coming off the liquid. And diethyl ether has the greatest of these 4. And diethyl ether used to be used as an anesthesia to knock people out because it has such strong vapors. So this is all based on intermolecular forces. So if we just compare these 4, water of course can hydrogen bond. Alcohol, because it has the OH group, can also hydrogen bond, but not as much as water. Bromine, or Br2, is a nonpolar compound, fairly large, but only London dispersion forces. Diethyl ether, while slightly polar, has fairly large nonpolar area, so it has weaker intermolecular forces, and is much smaller than bromine. So our 2 factors that are going to be important for vapor pressure are temperature and intermolecular forces. As the temperature goes up, so does the vapor pressure for every substance, because we're loosening up the intermolecular forces. The type of intermolecular forces can determine how much vapor pressure we get as well. The weaker the forces, the greater the vapor pressure is going to be, because less energy is needed to vaporize those liquid molecules into gas. The term volatile is used to describe those substances that vaporize easily. So volatile doesn't really mean explosive or even flammable. It just means it creates a lot of gas. Now that gas might be flammable, and that might be something to worry about, but the word volatile is really just talking about how easy is it for a substance to vaporize, and really how weak are its attractive forces, or intermolecular forces. So if we look at this graph, we're trying to determine which molecule is most volatile. So we're looking at vapor pressure on the y, and temperature again on the x. So we know that a volatile substance is going to vaporize easily, so it's going to have a higher vapor pressure. So if we pick any temperature, let's pick 40 degrees, and we move up, we can see that this substance to the far left is going to have the greatest vapor pressure at 40 degrees Celsius. This indicates that it's the most volatile. The others have much less vapor pressure because they have stronger forces. Alright, so let's compare substance A, B, and C. Again, we're looking at a vapor pressure graph, vapor pressure versus temperature. So which of the molecules in the graph is in the liquid phase at 400 millimeters of mercury and 50 degrees Celsius? So if we go to our graph, 400 millimeters of mercury, 50 degrees Celsius is going to put us right here. So we are below the line for substance A, but above the line for substance B and C. So we want to think about what that means. A is obviously the most volatile, so at 50 degrees, practically all of it is in the gas phase, because here's its line, okay? But for B and C, very little of it has vaporized at 50 degrees. And in fact, at 400, we're still in the liquid phase. So B and C would both still be liquids at this temperature, and A would be a gas. Alright, at higher temperatures, are molecules likely to be gases or liquids? Well, we can see as temperature increases, we get an increased amount of vapor pressure, indicating that as temperature increases, vapor pressure is increasing. Therefore, more of our liquid molecules are becoming gas. So they're more likely to be in the gas phase. At higher pressures, are molecules likely to be gases or liquids? Alright, so let's think about what's happening with the vapor pressure. Now, the vapor pressure here indicates the pressure from the molecule as it's creating gas molecules. So as we have higher pressures of the gas molecule, we know that more of it is being vaporized. But what's happening if the pressure comes from the outside? As we increase pressures on the outside, it's going to push molecules closer together, and they're more likely to be liquids. Alright, vapor pressure also affects boiling point. Now, we saw how boiling point is affected by intermolecular forces. But let's look at how boiling point is affected by vapor pressure too. So when we have a container of liquid, some amount of those liquid molecules are vaporizing to become gas. Some amount of those gas molecules are recondensing to become liquid. Now, the vapor above a liquid from the vaporization contributes to the vapor pressure of the substance. But there's also atmospheric pressure. Now, for most of us, atmospheric pressure is about 1 atm, or 1 atmosphere. As we go to higher elevations, that decreases. And if we go to lower elevations, it's going to increase slightly. Once the vapor pressure of a substance is equal to the external pressure, boiling occurs. So if we look at our water as an example, water at 90 degrees Celsius, which is below the boiling point, we have less vapor coming from the water compared to the air pressure. So our 1 atmosphere is the same as 760 torr, but our water pressure is only 525 torr. Because the pressure externally is greater than our vapor pressure, the external pressure is pushing down on our water, and most of it is still liquid. If we increase the water temperature to 100 degrees, now our water vapor pressure is equal to the atmospheric pressure, and this is when boiling starts to occur. Now it's a tie. There's no clear winner in terms of the amount of vapor and the pressure exerted. But if we continue to keep the water at 100 degrees Celsius, or even slightly above, we continue to add energy, the vapor pressure of the water increases to greater than that of the atmospheric pressure. Now more and more of the water is going to vaporize into the gas state, and eventually all of our liquid water will be gone. So if we look back at our vapor pressure versus temperature graph, we can determine the boiling point of a substance based on when its vapor pressure equals that of the external pressure. So 760 torr is our external pressure, this flat line going across. And if we look at our ether, alcohol, and water graphs, we can see that the ether crosses this line and has vapor pressure equal to 760 torr at 34.6 degrees Celsius. So this represents the boiling point for ether. Alcohol crosses at 78.4, and water crosses at 100 degrees Celsius. Alright, so let's look at how we can apply this information. If we have three different molecules, formaldehyde, fluoromethane, and hydrogen peroxide, we want to know which one is a liquid at room temperature. We want to use our idea of intermolecular forces because that affects our vapor pressure and our boiling point. So formaldehyde is a polar molecule but cannot hydrogen bond, so we would say it has dipole-dipole forces. Fluoromethane, also a polar molecule because of the carbon-fluorine bond, but it cannot hydrogen bond, so again dipole-dipole forces. But then hydrogen peroxide, as we saw in the previous video, can form hydrogen bonds. So these intermolecular forces for the hydrogen peroxide are going to be stronger, allowing it to stay at a liquid at higher temperatures compared to the other two. So hydrogen peroxide would be the liquid at room temperature. Now in terms of determining boiling point by ranking molecules, we want to think about intermolecular forces again. So we have an OH group here, so hydrogen bonding. We have an NH2 group here, hydrogen bonding. We have an ether group that has an oxygen with two carbon chains, cannot hydrogen bond, but is still polar. And then we have a hydrocarbon chain. Our hydrocarbon chain is nonpolar and can only have London dispersion forces. Our ether is polar and has dipole-dipole forces. Now both of these compounds can hydrogen bond. So how do we determine which of these would have the higher boiling point? Remember, we want to focus on the strength of the hydrogen bonding. OH is going to have a stronger hydrogen bond than NH because we have a greater electronegativity difference between oxygen and hydrogen compared to nitrogen and hydrogen. So our alcohol would have the highest boiling point. Our amine group would be number 2. Our ether group with only dipole-dipole forces would be number 3. And our hydrocarbon with only London dispersion forces would be number 4. Now we can make this comparison based on intermolecular forces because their molar masses are not that different. Alright, just a few little ideas about pressure. Atmospheric pressure is 1 atmosphere, which is the same as 760 torr or 760 millimeters of mercury. This is also the same as 101.3 kilopascals. You will be responsible for these conversions, right? The conversions shown in red. When a question asks for the normal boiling point of a substance, they're asking for the boiling point at 1 atmosphere, or 760 torr, or 760 millimeters of mercury, or 101.3 kilopascals. So the word normal is referring to that 1 atmosphere. Because remember that our boiling point can change if we change the pressure. Alright, Once we go to higher elevations, where atmospheric pressure is lower, the boiling point of our substance also lowers. Once we have lower elevations, where our atmospheric pressure is higher, our boiling points are going to be higher because we have a greater demand for the pressure needed for boiling. Here's a table that shows some information about this. So depending on the elevation that you are on the Earth, Mount Everest, water boils at 78 degrees Celsius because the atmospheric pressure is so much lower than what we experience. Even Mount McKinley and Mount Whitney have water boiling points in the 80s. Sea level, most of our coastal cities, would still have 100 degrees Celsius for boiling point. Here on Kennesaw Mountain, which is the highest peak in Metro Atlanta, our boiling point is still 99 degrees Celsius because we are not that far above sea level. Now, unlike boiling point, melting point is not affected by pressure. So melting point and freezing point are the same in terms of the temperature, and they create a dynamic equilibrium between our freezing and our fusion. But because they involve solids and liquid states, they are not affected by pressure. Okay, boiling point, because it involves a gas state, is definitely affected by pressure because of the compressibility. But solids and liquids are not compressible, and so pressure doesn't play a role. And when we plot this as a graph, like we had our vapor pressure versus temperature graph, if we plot pressure versus temperature for melting point, we see a line that has a nearly infinite slope. And what that means is the graph looks like a vertical line straight up and down, where pressure does not play a role. Sublimation. If you remember from our triangle of phase changes, sublimation is going from a solid directly to a gas. If you've ever seen dry ice in packages that are delivered where something has to stay cold and you open it up and there's these white blocks of dry ice and there's this vapor coming off of them. That's carbon dioxide subliming from the solid state into the gas state. Okay, and this is the same point as the deposition point. Because it's going from a solid to a gas state, again we have to factor in pressure. So when we put these three different things together, boiling point, melting point, and sublimation point, we can create what's called a phase diagram. So if we look at our phase diagram, we have pressure versus temperature. From this point down here, up this way, this is our boiling point line. So this is the graph we looked at earlier that was our vapor pressure line, or pressure and temperature, that's this one, where we see a boiling point where it crosses 1 atmosphere. Our melting point line is from this point up vertically. So this is our nearly infinite slope line. It's nearly up and down, so pressure doesn't play a role. And we can find melting point again where it crosses 1 atmosphere. Our sublimation line is this last line down here. This is where we have solid going to gas. And again, it's very similar to our boiling point line in that it is affected by pressure. So it looks almost exponential. This point where all three of the lines touch is called the triple point. At this temperature and pressure, all three phases can exist for a substance. We can find the melting and boiling points by looking at where they cross the 1 atmosphere line. And then we have another point up here called the critical point. The critical point occurs on the boiling point line, or the vapor pressure line, when the density of the liquid and the gas phases are indistinguishable, or we can't tell the difference between the liquid and the gas phase. So remember, to tell the difference between a liquid and a gas, we're looking at the attractive versus kinetic energy of the molecules. But at the critical point, those values are the same, and the density is the same. So it becomes a supercritical fluid. So supercritical fluids occur at the critical point and above. Okay, and this is where we can't distinguish between the gas and the liquid. So if we look at the first circle here, our liquids on the bottom, our gases on the top. If we increase the temperature and we increase the vaporization, so liquid molecules are becoming gas, eventually we reach a point at very high temperatures and high pressures where we can't tell where the liquid and the gas phases are anymore. They're indistinguishable. They become one supercritical fluid. And the supercritical fluid has the properties of both the gas and the liquid state. So if we look at the phase diagram for carbon dioxide, or CO2, we can find our lines. Here is our boiling point or vapor pressure line going up to the critical point. Here's our melting line, nearly vertical, and here's our sublimation line. And in the middle we have our triple point. So if we look at where 1 atmosphere is, we can see why we normally see carbon dioxide as only a gas. At 1 atmosphere, we only have 2 states, solid or gas. And if we look at the temperature, we know that we are normally closer to this end in terms of room temperatures, about 25 degrees Celsius. So CO2 is definitely in the gas phase. In order to get solid CO2, we have to decrease the temperature dramatically, below -78 to get it into the solid phase, and that would be dry ice. So this is why when you open your package, it immediately starts vaporizing or subliming. Now liquid CO2 doesn't occur until up here. So this green area is the liquid. And if you notice where the triple point is, the pressure has to be greater than 5.1 atmospheres in order to get the liquid phase, which really doesn't happen in our normal everyday lives because that's 5 times the normal atmospheric pressure. So this would only happen in a pressurized canister. But for every phase diagram, our solid is going to be on the left side at lower temperatures, higher pressures. Our gas is going to be on the right side at higher temperatures and lower pressures. Higher pressures get to our supercritical fluid. And the liquid is going to be in between those two. So if we can identify our lines, we will know where our solid, our liquid, and our gas phases are. This is the phase diagram for water, and we see the same areas of solid, liquid, and gas. We see the triple point, which actually does occur under the 1 atmosphere line, so we can see solid, liquid, and gaseous water. And we have the critical point way at the top here at very, very high temperatures and pressures. So we're not likely to see this ever. Now another thing that's important besides being able to see solid, liquid, and gas all at 1 atmosphere is that this line for melting point slants to the left. Usually it's fairly vertical, but if we look at the CO2 line is slanting slightly to the right, which is more normal for most substances. So why is the water line slanting to the left? This is actually a pretty unique property of water. And this tells us that as we increase pressure at a given temperature, so if we're looking at -1 degrees Celsius, as we increase pressure and move up the graph, we see that the material goes from a gas to a solid to a liquid. And at high pressures, water remains a liquid instead of a solid. So at high pressures, we're pushing molecules together. Why don't they form the solid lattice? Most substances form a solid at high pressures. Water doesn't. Water forms a liquid. Because if we push molecules as close together as possible, it can't form the solid lattice that we're used to. It only forms the liquid arrangement. This also indicates that liquid water is more dense than solid water. And we see that because ice floats. Alright, thank you for watching. This is the end of this video.